Monday and welcome back. We're going to dive right in today with two things that we didn't get to last time that I told you we would do today. Just going to spend a couple minutes on each of the topics. The first is reductive amination, which is not something new. It just combines two things you already know in a new way. So you already know that if you take an aldehyde or a ketone, you can react it with an amine and a catalytic amount of acid to make an imine. That's not new, that should be old and pretty straightforward to you now. And the effect is to add this carbon-nitrogen pi bond to the carbon, to make a new carbon-carbon pi bond and carbon-carbon, I'm getting all this wrong, sorry. To make a new carbon-nitrogen sigma and pi bond between the nitrogen and the carbonyl carbon of the aldehyde or the ketone. The thing that we're going to do that's new today is say, what if we were to add a hydride delivery reagent to the imine? The imine is still an electrophile. It is not as good of an electrophile as the aldehyde because nitrogen is not as electronegative as carbon. Nevertheless, if your reagent is reactive enough, you could imagine doing some of the same nucleophilic addition to carbonyls chemistry with imines as we've done before with aldehydes or ketones. So, if you add sodium borohydride and then some protic solvent like an alcohol, you can deliver a hydride from borohydride as a nucleophile to the carbonyl carbon. What that looks like is this. Here is the hydride that got delivered from the carbonyl carbon. Here's the new carbon-hydrogen bond that was made. I'm not going to draw that mechanism because if you go back and look at the sodium borohydride addition to a ketone mechanism that we did on the first or second day of class, it will be exactly the same, only the electrophile is the imine. That would create a negatively charged tetrahedral intermediate, but the nitrogen would then pick up a proton from the solvent to give you no longer an imine, but amine, amine, or amine. Nobody says amine. I guess sometimes the Brits say amine, but we'll say amine. Effectively, you have added the hydride and a proton, and you reduce the imine to the amine. So that reduction step is what gets you the amine, and that's why they call it reductive amination. In effect, this allows you to make a new bond, to put a second alkyl group on the amine nitrogen in a controlled way. We won't talk about this, but you could imagine starting with this amino nitrogen and just adding an alkyl halide to it. You could say, hey, let's just do the SN2 reaction. Doesn't that work better? Isn't that faster, more efficient? Turns out it doesn't work very well for reasons we don't need to talk about. So reductive amination is a preferred way of adding a single alkyl group to the nitrogen in a controlled way. Yes?
So basically we're taking a carbonyl and taking a primary amine and making it into a secondary amine?
That's right. Overall, if you look at it, we've converted a primary amine into a secondary amine. And it turns out you could do this again if you wanted to. You could do a second round of reductive amination to turn a secondary amine into a tertiary amine. You could install different alkyl groups in this way. Okay, so that's probably enough on that. The second thing we need to talk about is the Wittig reaction. The reason it doesn't fit that neatly into chapter 14. The reason it fits is because the starting material, one of the starting materials, is an aldehyde or a ketone. And the other reason it's in this chapter is because it had to go somewhere, it's synthetically useful, and it's a Nobel Prize winning reaction. Organic chemists, the chemist who invented the reaction was German, so we say the Wittig reaction with a V sound instead of W. If you say the Wittig reaction, organic chemists are going to twitch a little bit, so if you want to do that passive aggressively and see what happens to me, you can. It'd be kind of interesting. The starting material is either an aldehyde or a ketone, and that is the electrophile. So that's the common theme in chapter 14. The other partner, the nucleophile, is going to be called a couple of different things. It's called the Wittig reagent, that's easy. And then another term for that Wittig reagent is a new word you probably haven't heard before, and that is YLIDE, the ylide. I'm going to draw an example of an ylide reagent here. It's got a phosphorus. The phosphorus is bonded to 4 carbon groups, in this case 3 nitrogens, and then one of the carbons that the phosphorus is bonded to is deprotonated and is negatively charged. We call this an ylide because it has a negative charge and a positive charge on adjacent carbons. Sometimes people will draw this ylide based on the idea that phosphorus can have more than 4 bonds. It's a third row element, and third row and beyond can have more than 4 bonds. So they will take the lone pair on the adjacent carbon, they'll kick it down to form a pi bond with phosphorus, and then they'll just draw the rest of the phosphorus reagent like this without a positive formal charge on the phosphorus. Either of those 2 forms is totally fine. Your text will most often draw it like this. So you need to get used to seeing both and recognizing both as just a Wittig reagent. Now, we don't have time today for the mechanism for this reaction. It's not that hard, but the payoff is not that great for knowing it, so we're just going to skip it. If you want to know more, you can ask me about it in office hours, and I'll tell you. It's actually not that difficult. You can imagine the negatively charged carbon acting as a nucleophile to attack the carbonyl carbon, and that's exactly what happens. There's some other things that happen as well. Let's keep track of a few things. The blue carbon and the purple carbon. The product of the Wittig reaction is an alkene. And we'll draw that alkene structure here. Here is the carbonyl carbon. Here are 2 new bonds that you make. The first is a sigma bond, the second is a pi bond. And then what do you make them to? You make those 2 new bonds, sigma and pi, to the purple carbon of the ylide. And I've drawn the trans stereoisomer, but you would also get the cis stereoisomer. Probably you would get more of trans than cis because the trans stereoisomer is more stable than the cis stereoisomer. The other portions of the molecule, what else happens here? Where does the oxygen go? Here's the carbonyl oxygen, and then I'll use maybe orange for the phosphorus. The other product of this reaction has the phosphorus bonded to the carbonyl oxygen. And then, of course, the phosphorus is still bonded to its 3 phenyl groups. That molecule is called triphenylphosphine oxide, and the new sigma phosphorus oxygen and pi phosphorus oxygen bonds are very strong, and that provides a strong driving force for the reaction to happen. In a way, this is a sort of Lego click type reaction in the sense that you pull apart the carbonyl carbon and the oxygen, you pull apart the phosphorus and the carbon, and you stick them together in a new combination. All right, questions so far about that reaction? That's starting materials, predicting the products. Okay, yes?
Are both the sigma and pi phosphorus oxygen bonds strong?
Yes, yeah, both sigma and pi are strong. Okay, so the Wittig reaction makes a new carbon-carbon sigma and pi, 2 new carbon-carbon and sigma, carbon-carbon sigma and pi bonds, and then you make 2 new phosphorus oxygen sigma and pi bonds as well. It's useful, this reaction is useful because it takes 2 different pieces and brings them together. That's called a convergent process, when you can synthesize 2 carbon chains and then connect them together at a late stage. It's good because you make 2 new carbon-carbon bonds, as I've said. you can start to think about it in terms of retrosynthesis, and we'll do this briefly, and then you should practice this. Let's just imagine we look at this and we say, anytime now you see an alkene, you can think, hey, I could have made that carbon-carbon sigma and pi bonds via the Wittig reaction. And there may be two different ways you could envision doing this. One would be to have the carbonyl carbon be the one on the right. Sorry, I get my right and the left wrong every time. Have the carbonyl carbon be the portion of the molecule on the left. And then the portion on the right would look like this. And I'm just going to draw the Wittig reagent in the sort of simplest way with the phosphorus carbon double bond. Okay, that's one option where the nucleophile is here on the right and the electrophile is here on the left. You could also envision an alternative in which the carbon on the left is the Wittig reagent, and then the carbon on the right is the carbonyl electrophile. Now, either of those look reasonable. It turns out that one is better than the other, and the better option is this one. And I want to show you the reason why. It has to do with how you synthesize the Wittig reagent. So to show you this, we're going to start with an alkyl halide like this, same number of carbons as the Wittig reagent, 1, 2, 3, 4, 1, 2, 3, 4. The first reaction is an SN2 reaction using triphenylphosphine. That's the phosphorus bonded to 3 phenyl groups. And importantly, our starting alkyl halide is a primary alkyl halide, which means the SN2 reaction is especially fast and efficient. The molecule that you make after that first step looks like this. It has a positively charged phosphorus. This is called a phosphonium salt. And it is then, to make the Wittig reagent, you simply have to remove a proton. You've got 2 protons on that carbon that's bonded to the phosphorus. We're going to remove a proton using a really strong base, and the common base to use is called N-butyl lithium. You need a base that's strong enough to remove an sp3 hybridized carbon-hydrogen bond. And if you're not seeing where that proton gets removed, I'll draw the alternative resonance structure of the phosphorus of the Wittig reagent so that you can see it. So the idea is, we don't have time to draw it out, but if you did this and followed this through, making this Wittig reagent would require an SN2 reaction with a secondary alkyl halide, and that's simply less efficient and slower. So the moral of the story is, if you have a choice with the Wittig reaction, if you can choose to make one portion of the molecule a Wittig reagent, you should choose the side that's less substituted, so that the SN2 reaction you use to make that Wittig reagent will be faster and more efficient. Does that make sense? Yes? So why do we go with the less substituted one? Is that your question?
What do we do with the least substituted one?
You want to choose the side that's less substituted to be the Wittig reagent, so that you can make that via the more efficient SN2 reaction. Okay, so you can imagine me writing a question where I say, which is the best way to make this reaction? Which is the best way to make this alkene via the Wittig reaction? And I show you all the options, and you'll be tempted to choose this one because you're like, that would work, but there's a better choice. Okay, I feel like I'm revealing all of my evil tricks early, but that gives me a chance to monologue about my evil, which you know that all villains cannot resist, and it gives you a chance to prepare in advance, so it works out. Okay, that's chapter 14. So now we want to move on to chapter 15. Chapter 15 is a couple of things. It's a review of acid-base chemistry. And it's also some stuff on nitriles. The nitriles are sort of crammed in there because of a revision of the text and they didn't know where else to put it. We're not going to spend very much time on the nitriles. Your study guide will have you learn 4 reactions of nitriles using nitriles as electrophiles. Maybe next time I will summarize those real briefly. We're not going to worry about the mechanisms. You just want to be aware of the reaction, the starting material, the reagent, and the product, so that later on in the class, if the reactions crop up in various practice problems, you know what to do. We're going to spend most of our time on, because keeping track of reagents is not as hard as what we're going to spend our time on. So we're going to spend our time on talking about using acid-base information to understand what good leaving groups are, and also to understand how complicated biomolecules should look as a function of pH. So we're actually going to start there. Chapter 15, basically predicting what I'm going to call protonation state of a biomolecule as a function of pH. And in so doing, we're going to use something that you learn in general chemistry that you hoped and prayed you would never encounter again, and yet here it is, the Henderson-Hasselbalch equation. I know, isn't it lovely? Here's the thing. You use this in general chemistry, not in the way that we are going to use it, and our use is going to be simpler and maybe even more meaningful. When you were, and I know this because I had a son that just took Chem 105 before his mission, and he was in my office all the time 1 year ago, and we were talking about Chem 105, and it was a stressful experience for him. So I know where you've been. In Chem 105, you used, or maybe it was 106, I can't remember, what do I know? You used this equation to answer the question, I want to make a buffer, and I want the pH to be 7.5. I want to use this buffer, I want to make this buffer using phosphoric acid. How much of the monosodium phosphate versus the disodium phosphate should I mix together to get a buffer of that pH, right? That sound familiar? Getting some PTSD? Yeah. Or perhaps you used it in this way. I mix these two acid and its conjugate base together in this ratio, and the pKa is this. What is the pH that I get out? And you can do that math. Now, this class is not heavy on math, and we will not be doing that type of math. If you can count, if you can divide by 2, and if you can do greater than, less than, you're good to go. The one thing you might need is a vague recollection of properties of logarithms, but not even that detailed on this. We're going to use this equation not to predict making buffers, which is useful but sort of boring. We're going to use this equation to ask the question, if the pH is constant, as is the case in biology, and if the pKa's of various acids are known, what should be the ratio or the relative amount of conjugate acid versus conjugate base in solution at any given time? Let me show you how this plays out. Imagine a very scary large biomolecule, okay? And imagine there are groups hanging off this biomolecule that have the potential to be acids or bases. So there's a carboxylic acid. There's an alcohol. There's a thiol. There's another alcohol, only this one's a little bit different because it's attached to a benzene ring. I could think of some other ones, but that may be good enough to get started. And suppose I tell you that this molecule is dissolved at a low concentration in a solvent or buffer that has pH fixed at 7, say the interior of a cell, or say blood. Now, you could argue, well, isn't it actually 7.4 or whatever? Fine, I don't care. We're just going to say what the number is. and we're going to choose to one significant figure, all right? There's another term you didn't want to hear today, significant figures. All right, so what you would do to predict, and the way I would ask this question on an exam would be draw the horrible molecule and then tell you what is the net formal charge on this molecule at pH, whatever, in this case 7. So you'd have to go through and identify all of the groups that could either lose or gain a proton and decide as a function of pH whether that happens or not. Let me take you through this. Let's start with the carboxylic acid, which is easy because it's a carboxylic acid, so you can recognize it. What I would do is draw the conjugate base. Then I would look up the pKa information for the neutral carboxylic acid going to the negatively charged conjugate base. And I would see, if I did that, that the pKa is 4. Now, here's how to apply the Henderson-Hasselbalch equation. 7 minus 4.
Wait, isn't it 4 minus 7?
What?
The pH is 7.
Oh, fine. Yes, you're right. pH is 7. Okay. Actually, sometimes, this is dumb, but it's not really dumb. It's just my life. One of my children in the past year has been diagnosed with ADHD, and it's something that we just thought this was sort of their normal personality, and then there are things that sort of crop up. And as that's happened, I've started to notice it in myself. So I'm actually going to the doctor tomorrow to talk to him about it. It happens. So this water bottle, for example, I lost yesterday during church. I left it in the teacher's quorum. I'm a teacher's quorum advisor. I left it in that room. But see, I didn't remember setting it down. And by the time I realized I lost it, I thought I had left it in the chapel. So not only did I lose it, but I actually lost it in the wrong way. Anyway, one of the things I'm noticing about myself is my brain stops paying attention while the words are coming out. And so sometimes I'll do things like I just did with the 4 and the 7. So there you go, man. The other fun story I have recently was the time I was in Costco. And you know how you have to scan your card to get into Costco now? So I obviously had the card on me and scanned to get in, but by the time I got to the checkout, I could find it nowhere. And literally, I'm sitting there for a not comfortable amount of time, right? Like, people are standing behind and they're starting to be like, "Let the paying customers through, sir." And the nice people at the desk were like, "Oh, it's okay, you can keep searching." And I'm doing the whole... And I had searched several times in my wallet, and then I finally find it in my butt pocket after all of this time. So anyway, got issues, but that's the explanation apparently for why I said 7 and 4. I'm sorry. Please correct me. I'm glad you're paying attention, because on some level I'm not. All right. We just spent way too much time on that. I'm really sorry. We need to get going, but... You guys actually, I know you don't mind when we burn valuable class time on no content. I know that that's okay with you, right? All right, so we're back. So 4 minus 7 is a negative number, right? Greater than, less than. Okay, now you need properties of logarithms. If this is a negative number here, which of the two is bigger, the numerator or the denominator? Denominator, right? If a log is negative, that means the number inside the log is less than 1, right? So that means the conjugate base form dominates. Now, some of you like equations. You think in equations, and that's great. I know some of you don't, like that's hard. So here is the answer in words. If the pKa is lower than the pH, the conjugate base form dominates, or the acid loses its proton. I'll say that again in case you want to scribble it down. If the pKa is lower than the pH, the conjugate base form dominates, or the acid loses its proton. So, with that in mind, which form for the carboxylic acid should be the dominant form at pH 7? Negatively charged conjugate base. Okay. Let's do the alcohol. If you looked up the alcohol, it has a conjugate base that's negatively charged. Its pKa is 16. 16 minus 7 is a positive number, which means what? The acid form dominates. Or, if you like it in words rather than equations, if the pKa is greater than the pH, the proton is still on. Yes?
Will we always be given the relative pKa values of each of the compounds, or?
Yeah, so you're going to be given a pKa table, which if you go on Learning Suite now to the content page and click on pKa, IR, and NMR table, you can see in exact detail what to expect for what you'll be given. Two numbers that you need to memorize are 16 and minus 2. That's the pKa for alcohols, or also, and then minus 2 is for H3O plus and protonated alcohols. And speaking of protonated alcohols, there was one thing you were not worried about somehow, instinctively. You were not worried about the alcohol picking up a proton from the water or the buffer to generate its positively charged conjugate acid. Now, it turns out that failing to worry about that was inconsequential here. Why? Because the pKa of that protonated oxonium ion is minus 2. So do the math. Minus 2 minus 7 is still a really large negative number, meaning that at pH 7, the oxonium ion loses its proton to give you the neutral alcohol. Does that make sense? Let me show you a situation where failing to think about the neutral molecule gaining a proton will have consequences. Let's look at this amine here. If you looked up at a pKa table, many of you would, because you'd be thinking about losing protons, many of you would find that the pKa for the neutral amine going to the negatively charged conjugate base is 38. And you would have compared 38 to 7 and concluded that that proton is still on. And you were right. Never in the age of the universe has an amine group lost a proton to water. It's no contest. But if you forgot that the amine also has a positively charged conjugate base called the ammonium ion, you're going to see that that does have consequences. The positively charged ammonium ion has a pKa of 11. Again, do the math. 11 is greater than 7. If pKa is greater than pH, that proton is still on, which tells you that at pH 7, not only does the neutral amine not lose a proton, but it must gain a proton to become the positively charged ammonium form. Where does it gain the proton from? Well, from the H3O plus that's present in pH 7 water. Okay? That pKa of 11 is telling you just how reactive the amine is as a base, that it can pull a proton off of the H3O plus that's present at pH 7 water. Okay? The reason this is hard is because I'm not going to show you the ammonium ion. That would be too easy. I'm going to show you the amine, and you're going to have to realize by looking at the pKa table that this ammonium ion is relevant. Okay, questions about that? We're going through it slow because students get this wrong all the time. And honestly, if the question is, what is the correct formal charge on this molecule? It is not good enough to be almost there. It is not good enough to basically understand the concepts. You have to get all of it right, each and every one. So this is why we're talking about it. Questions? Yeah?
So whenever the pH is greater than the pKa, it has the extra proton on it?
When the pH, no, we got that exactly backwards, yeah. That's why I always go back to the equation, because as I told you, my brain fails to pay attention to the words and then I get it wrong. If the pKa is greater than the pH, then the proton will still be on. Yep. So yeah, that tells you, that's why you should pay attention for the neutral amine, not only to the pKa for losing a proton, but the pKa for the positively charged conjugate acid. Yeah.
So a couple questions. The PKA things as you add more hydrogens, right? As a general rule.
I'm sorry, you said the pKa increases as you add more hydrogens?
Decreases.
I think that's true.
Okay, and so we basically keep adding hydrogens until we get a sort of positive number in the Henderson-House plot equation.
I think I'm not sure if that's true. So I'll let me just summarize briefly the process, and then if you have more questions about that, let's talk after class.
I mean, like, until you get a negative number. So it's basically the most hydrogens with that you can put on while maintaining the
So what I would recommend instead of that is that you look for this molecule in the pKa table. If you can't, and then look for numbers. All right, let me just be really clear. I'm going to look up whatever group I think can either gain or lose a proton on the pKa table. I might not find it, but I'm going to look for it. For example, for this amine, I would find not only that this amine has a pKa of 38 to lose a proton, but I would also find the conjugate acid of this amine as this ammonium ion with a pKa of 11. So use the pKa table to help you realize what's important. Yep. Okay, couple more that, yeah, go ahead.
Now, if we were to look and it were to have a lower pKa than, say, 7 in this, or than the 7 in this case, we would not have something.
Right, so classic example of that. If a pKa were, if you looked up something that had a positively charged conjugate acid and its pKa were lower than 7, then yeah, you wouldn't add the proton. Classic example of that is this neutral group that's called imidazole, and this is the amino acid histidine. It's got a positively charged conjugate acid whose pKa is 6. That positively charged conjugate acid looks like this. By the way, I'll just interject that you want to use the pKa table to find the thing that is most structurally similar, right? So I'm looking at this. I would actually find the conjugate acid on the pKa table. Its pKa is 6, and you are right, at pH 7, that should be neutral. Yep. Okay, we can go through and do some of the rest of these. For example, this alcohol has a pKa that is 10 because its conjugate base is resonance stabilized, so its pKa is lower than you would expect for a typical alcohol. But again, at physiological pH 7, pKa is greater than pH. That means the proton is still on. Similarly with this sulfur, the conjugate base is called a thiolate. It has the thiol has a pKa of 8. 8 is greater than 7. You'd predict that was neutral. So you'd go through this one by one, assigning pluses and minuses, and then you would total them all up, and that involves a little bit of addition. So that's the other math you got to be able to do. And then to get the right answer, you need to select the right one. And the options are going to be +5, +4, +3, +2, +1, so and -1, and so on. So you want to make sure you can do this right 100% of the time. One more group that is sometimes confusing to people. These are all amino acid side chains, by the way. Is this side chain. It looks like it's 3, it looks to students when you first see it like it's 3 different amino groups, but it turns out it's not, because all 3 amino groups are involved in resonance with each other. You should be able to see that I could easily move these lone pairs down to form a pi bond here, break this pi bond and move the lone pairs out there. So these nitrogens are conjugated with each other. They are one functional group that's called guanidine. And you'll find not this on the pKa table, but its conjugate acid. And I'll draw the conjugate acid for you. It involves one of the nitrogens picking up one more proton and becoming positively charged. And you can see by resonance that that positive charge is delocalized onto all the other nitrogens. The pKa for that positively charged functional group, it's called guanidinium, is around 12. So you would conclude at physiological pH that this should be positively charged. I've seen a student make a mistake before where they thought that that was 3 different nitrogens, and so they thought the thing had a +3 charge, and it's not. It's one functional group that can pick up one proton to have a pKa of 12. Okay. All right, so that's going to take some practice. I encourage you to work through that. A pKa table is available. You can create problems on your own simply by drawing a squiggly line and then picking things off the pKa table and seeing if you can get it right. Yes?
Sorry, just the guanidine, so it's pH 12, so the pH of 7, it's going to keep the proton?
That's right. The guanidinium has a pKa of 12. At pH 7, it will keep its proton. Or if I drew the neutral guanidine, you'd have to say at pH 7, it's going to steal a proton from H3O plus to become the positively charged guanidinium. All right. Yes?
Just to clarify, the overall charge, like what you've drawn, would be 1, correct?
Let's see, now I got to count. +1, -1, +1. So yeah, overall net 1. All right. Now what we're going to do is take a minute to, I think, review something from general chemistry that's going to be useful in understanding biological macromolecules, and this is to think about phosphoric acid. There's something that you hope that you would ever encounter again. Unfortunately, phosphate groups are all over the place in biology, so it's worth thinking about them. This is neutral H3PO4. And the process by which it loses a proton has a pKa of around 2. We're just going to stick to one significant figure. If you tell me actually the pKa is around 2.2, I will say, I know, it's in my notes, and I chose not to write it because I'm sticking to one significant figure. So going from the neutral H3PO4 to the monoanion has a pKa of 2. Going from the monoanion to the dianion has a pKa of 7, and then going from the dianion to the trianion has a pKa of 12. So if pH is around 7, what 2 forms are dominant of phosphoric acid? Mono and dianion, right? In fact, you expect about a 50-50 mixture of these 2. That's important because in biology, when we're going to use phosphate groups, it's going to be fine to draw them either with 1 negative charge or 2. Both are reasonable. And you'll see me go back and forth between that as is depending on what's more convenient without explanation. And if you want to know why, the answer is both of those forms are relevant at physiological pH. Let's use that real briefly to think about leaving groups. If you remember, when we started this class, we ranked carbonyl compounds in terms of reactivity. And up at the top, we had things like aldehydes and ketones, which don't have good leaving groups, but are really electron poor because the Y groups in yellow are really not good electron donors. But then we also had things that had good leaving groups. For example, we had acid chlorides, we had anhydrides, and then we had thioesters. And you can recognize these as good good reactive carbonyl compounds because the things highlighted in yellow are good leaving groups. And we knew that they were good leaving groups because their conjugate, because once they left, you could see that their conjugate acids were fairly strong acids. For example, HCl or a carboxylic acid. pKa of HCl is -7, pKa of the carboxylic acid is 4. We would see that the thioester, the leaving group, is a thiolate, and the pKa of its conjugate acid is around 8. And so you can use this information to rank among these, just a second, in terms of reactivity. You would predict that the acid chloride is more reactive than the thioester just based on leaving group ability. Okay, go ahead.
When the pKa is equal to 7 and the pH is 7, that means it's 0. Because it's like
That means it's, yeah, if, going back to that equation, if this, oh, we scrolled too fast. If this number is 0, that means this number is 1. That is an even 50-50 mixture of acid and conjugate base. Okay. So we're used to things being decent leaving groups for highly reactive carbonyl compounds where the leaving group has a conjugate acid whose pKa is in this range. The phosphate group has a pKa in this range, so you might expect the phosphate group to be a decent leaving group. So we're going to introduce a new functional group, the acyl phosphate. So imagine having a carbonyl carbon that's attached to a phosphate group. In this case, I'm going to choose to draw it as this. There's other types of acyl phosphates. If we replace that OH group with an OR group, and we're not going to say what that OR group is, let's just think about that. What's the leaving group? Well, it's, in this case, the dianion. Or I suppose over here, it would still be the dianion. And though I'm not going to draw the conjugate acid, but because we've drawn it above, the conjugate acid has a pKa of 7. What that means is that this phosphate group is at least as good a leaving group as the thiolate, which means the acyl phosphate is at least as reactive as a thioester. And indeed, you will see later on in this semester that nature will use acyl phosphates to do nucleophilic acyl substitution reactions very similar to how nature will use thioesters. So this is a new type of functional group you're going to see in the future. You need to be comfortable looking at the phosphate and saying, okay, that's probably a decent leaving group. Okay, questions? Let's do, go ahead.
so this has so why do we say it's a good leaving group?
We say it's a good leaving group because we draw it after it leaves as the dianion. Then we would draw the conjugate acid, which is the monoanion. We would look up the pKa of that monoanion, which is 7, and we would recognize that that leaving group is about as good as, say, the thioester leaving group that we have above, and therefore they are similar in reactivity. Okay, I want to just take the last couple of minutes and show you how you can reason through protonation states of organic compounds that have phosphorus in them. I'm going to introduce a new functional group called the phosphoester. These you will see all the time in biology. Last time we spent a fair amount of time drawing a carbohydrate in its chair structure, so here we go again. This is a phosphorylated version of glucose. This is called glucose 6-phosphate. Now, notice here that glucose 6-phosphate, as I've drawn it, is a monoanion. So scroll back up. Let's scroll back up in just a second to the phosphoric acid pKa's and see if you can guess what the pKa of this proton should be. I want you to see that the only difference between this and the monoanion of phosphoric acid is this oxygen here is an OR group. Okay, so scroll back up to the phosphoric acid pKa's. Take a look. Your choices are 2, 7, or 12. What do you think is the right pKa for this monoanion? 7, right, because that's the one that goes from the monoanion to the dianion. So we can draw the dianion form of glucose 6-phosphate. It's going to look like this. And now that OH group has lost its proton, if the pKa is indeed 7, at pH 7, how much of the monoanion versus the dianion do I have? Yeah, it's got to be around 50-50. So you're going to see textbooks, probably most of the time in biochemistry, they're going to draw it this way. That's fine, and you should be totally comfortable with that. And you should also be totally comfortable with that if it's drawn in the monoanion. Okay? One more example that you will see in biochemistry has to do with nucleic acids. In fact, here we're going to do a functional group called a phosphodiester. And this is what you see a lot in RNA and DNA. So here is the phosphorus, and I'm going to draw it in its neutral form. And you don't want to know this, but I'm going to draw it anyway. This is a ribose ring. We're going to abbreviate the nucleobase adenine as A. Squiggly line's going to indicate there's a whole rest of the molecule there. Then we're going to draw another ribose ring here. Let's let this base be G. And squiggly line indicates a whole other something there. Now, notice that I've drawn this phosphodiester in its neutral form. The phosphorus is bonded to an OR group, a second OR group, and then an OH group. Recalling those phosphoric acid pKa's, if you need to look up, turn a page and look in your notes to see them, what do you think is the right number for that? What is the right pKa for that proton? Should it be 2, 7, or 12? 2, right? Because 2 is for going from neutral phosphoric acid to the monoanion. Even though this isn't phosphoric acid, we've basically replaced 2 of the OHs in phosphoric acid with an OR group. So it stands to reason that, yes, the pKa for that is around 2, meaning at physiological pH, and I'm going to abbreviate the structure, you expect which form to dominate, the negatively charged form or the neutral form? Negatively charged, exactly. And you will see always in DNA and RNA, the phosphodiesters are negatively charged 100% of the time. Okay. Now, a couple of things. We have not talked yet about the nitrile reactions. I will spend almost no class time on them. If you want to do the portion of the study guide about them, you should. We won't have a lot of time to talk about them. I'll maybe mention them briefly at the next class. Second, logistics. We are needing to do chapter 16. I had intended to have 3 class periods on it. We have 2 before the exam. We're going to get to what we get to, and what we don't get to won't be on the exam. It will be on the next exam. I'll have maybe a little bit more to say on Wednesday about that, so just stay tuned. In the meantime, be working on chapter 16 as though we're going to get to most of it. Okay? See you on Wednesday.